All right, I want to welcome everybody on board here. Today we're going to talk about Advanced Hydraulics 2, and we're going to continue the thought of how does the water get through that pipe, okay? Remember, we were exploring the fact of how water moves through a pipe and what happens if we're not careful with it, all right? So we're going to start out by talking about total dynamic head. We left off last time talking a little bit about the water movement and friction loss. So now we're going to take that a little bit further. When you look at total dynamic head, there's two sides to a pump. There's the suction side and the discharge side. So we're going to look at the suction side first. When you look at suction head, you're looking at static suction lift. Static suction lift is going to be measured from the datum plane of the pump to the static water level. Now, some people call it a standing water level, okay, whatever it happens to be. And then the next thought here is, let's take a look at the suction side friction loss. Suction side friction loss is measured from the bottom of the pipe to the suction hole. And this is why it's important to be careful with just exactly how much pipe you've got going out to your supply source. Because if you've got too much pipe going out there, that's going to create a lot of friction loss, and we want to keep that friction loss to a minimum, especially on the suction side. All right? The next thing we want to look at is drawdown. Remember what drawdown is. Drawdown is the working level of the well. And so it's how far that water is going to draw down so that what's going in equals what's coming out. Now, on the discharge side of the pump, we're going to work a little bit differently. We're going to look at something called static discharge head. And you'll notice in parentheses there, we've got elevation. And static discharge head is measured from the datum plane to the highest point that we want to pump that water. Again, we can't forget that even on the discharge side, we're going to have friction loss. I would assume that there would be more friction loss on the discharge side than on the suction side, simply because there usually is more pipe on the discharge side than the suction side. Again, it's important, though, to try and keep that friction loss to a minimum, simply because the fact that it's going to rob you of pressure. And so the less friction loss you can have on either side, the better it's going to be for that pump. Now, the last thing we're going to look at here is the head or pressure requirement. Now, notice what it says, at the point of usage. So we're going to put a point of usage in here, and what we're putting in is the sprinkler head, and we're looking for 40 psi at that sprinkler head. This could be hooked up to a tank going into a house, and then that would be the point of usage. So your point of usage is where you want your pressure at, and then that head or pressure requirement is all determined on what you're trying to accomplish. With, of course, the sprinkler here, we're just trying to put a spray of water out at a certain radius, and so we need a certain amount of pressure to accomplish that task. In a house, you're looking at 30, 50, 40, 60 pressure regulation there, so that way you wind up having the ability to turn the pump off for a while. With the sprinkler system, you're going to have that pump on all the time. Now, in our next slide here, this curve represents what we call net positive suction head. And you see I have those letters in red there because we call it NPSH. There are two sides to NPSH. There's what's available and what is required. And right now, we're going to talk about NPSHR, the required head. It's the amount of head required by the pump to keep the fluid in a fluid state. I've always said the simpler way to say that is how much head is required by the pump so that way we prevent cavitation. All right, so we're looking at required. Now, this curve has actually 4 different curves in it. You see the first one there says power. All right, you'll notice it goes from the left-hand side of the curve to the right-hand side of the curve, and as it moves, it generally moves in an upward direction. All right? I'm going to generally speak about these next curves here, and then we'll individually take them one by one so we can see a little more about them. So the head curve and the flow curve are the next curve that we're going to look at. It is just one curve, and you can see it goes up to down, and that's because as your flow goes up, your pressure is going to go down. So the more water you try and push, the less head you're going to be able to produce. All right? The next curve here is called the efficiency curve, and you can see by looking at the efficiency curve that it really is more of a horseshoe almost like. And of course this curve is designed to show you that there is a point on the curve where it's the best place to operate the pump. And again, we'll talk more about that as we get into these individual curves. The last curve that's on there is called NPSH, net positive suction head required. And you can see this curve again moves in an upward direction. As your flow goes up, the pump requires more NPSHR. So we're going to take a look at each one of these curves, starting with the head and flow curve. So if we look at the head and flow curve here, you're going to notice the yellow line. It represents 87 gallons a minute. Okay? So our flow is on the bottom, and you can see we're pumping 87 gallons a minute here. And if we look over on the left-hand side, that's where the head is. So right now at that particular point, we're doing 87 gallons a minute at 130 feet of head. Remember that as our flow goes up, our head is going to come down, and of course vice versa. As your flow goes down, your head goes up. All right? The next curve we're going to look at here is called the efficiency curve. Efficiency curve. The efficiency curve really helps us to understand where the best point is to use our pump. And you'll notice our 87 gallon a minute line here, it's red over here in percentages of efficiency. And you'll notice that our 87 gallon a minute line here crosses at the zenith, or the highest point of that curve. And if we look across there and draw a line right straight across from that highest point, we're going to find that we're at about 62% efficient right there. Okay? Now, of course, we're going to recommend that you stay within 5 percentage points of what we call the BEP, or best efficiency point. Now, of course, it can't be 5 percentage points up or down, because then that wouldn't be the best efficiency point. What we're really talking about here is 5 percentage points on the high side of the flow, or 5 percentage points on the low side of the flow. So to calculate that, we're going to subtract 5 from 62, and of course we come up with 57. So now if we take and draw a line at 57%, you're going to notice that we go through that efficiency line twice. Once on the high side of the flow, once on the low side of the flow. If we go ahead and draw a line straight down the low side of the flow, we're right about there. If we draw a line on the high side of the flow, that puts us right about there. Now, of course, if we were to give some numbers to that, we would find that the low side of the flow is actually about 55 gallons a minute. When we look at the high side of the flow, that's going to come in somewhere around 120 gallons a minute. All right? Now, what we really mean here is we've got a minimum of 120 and a maximum of 120 and a minimum of 55, a range that we can work in. Now, remember, best efficiency means that we are paying the least amount of money to get the most amount of water. And of course, what we're really looking at here is gallons per minute per kilowatt hour, because we're looking at an electric motor here. So when you look at gallons per minute per kilowatt hour, and you stay within this range, you're paying the least amount. Now, does that mean that the pump won't do, say, 40 gallons a minute? Well, sure it will, but notice you're at 50% efficient. Will the pump do 150 gallons a minute? If the suction conditions are right, but again, now you're only at about 38% efficient. All right? So watching your efficiency can really help you because that's where your customer's going to save money at, all right? Now, when we have the regular curve in the curve that we were looking at was out of our larger pumps. This curve comes out of our water system pumps. This is a sprinkler pump here, a PD series pump. And you'll notice there that red line indicates what we call our recommended operating range, okay? There are 4 horsepowers here. The E is a 1 horse, F is 1.5, G is 2, HG is 2.5. And you will notice that this is recommended operating range. And so if you look at that 2.5 horsepower pump, you'll see that the recommended operating range for that is going to be 78 to about 24 gallons a minute. When you go down to the 2 horsepower pump, now we're looking at 66 to about 21. You get to the 1.5 horse pump, and it's 64 to 18. And then we finally get to that 1 horsepower pump, and now we're down to about 53 to 16. So those are the ranges that we would recommend that this pump be put in. And again, you'll see there's not an efficiency curve on these smaller pumps, but when we give you that recommended operating range, that helps you understand that if you cut about in the middle there, between 78 and 24, you'll find about the best efficiency for that 2.5 horsepower pump. All right? Now, the next curve we're going to look at is called the power curve. Power curve. It's red over here in horsepower. All right? And you're going to notice that at our 87 gallon a minute line here, we are operating at right around 5 horsepower. Now, what does it actually mean? Well, there is a formula to be able to calculate what the horsepower is, and the formula goes like this: gallons per minute times total dynamic head times specific gravity divided by 3960 divided by the pump efficiency equals the brake horsepower. The simple definition of brake horsepower is the amount of horsepower required by the pump to do the job that we want to do, which means, of course, it's going to vary based on what we're pumping. At 87 gallons a minute there, you can see it's about 5 horsepower. We've already talked about gallons per minute and TDH. Let's talk a little bit here about SG. SG stands for specific gravity, and the specific gravity of fresh water is 1. Now, the reason it's important that we understand the specific gravity of fresh water is 1 is because if we're pumping something different and it has a different specific gravity, that's how we're going to calculate what the horsepower will be required for that. For example, if I was pumping salt water, seawater weighs 1.2 times that of fresh water. And so therefore, I would need another 20% of power to do the same job. If I was pumping gasoline, gasoline's about 80% of fresh water. And so therefore, I would require 20% less energy to do the same job. And that's why it's important that we understand about specific gravity. Remember, 1 times any number equals that number. I know every once in a while I'll get somebody to say, oh yeah, 1 times 20 is 20. Well, yeah, okay. They'll say 1 times 20 is 1. No, it's not. It's 20, that number. So just remember that. 3960, where does 3960 come from? 3960 is a constant that we use. It's a way of converting gallons into brake horsepower, is the way that I like to explain it. Now, to do that, you have to understand that 1 horsepower equals 33,000 foot-pounds per minute. That's one of the many definitions of horsepower. Okay? If we were to take that 33,000 foot-pounds per minute and divide it by the weight of 1 gallon of water, we would come up with 3359.68, which, of course, we're going to round off to 3960. All right? So the next thought then is this. As our flow goes up, so does our horsepower requirement. Why does that happen? Because at 10 gallons a minute, we're asking the pump to push 83.34 pounds. At 100 gallons a minute, we're asking the pump to push 833.4 pounds. And at 1,000 gallons a minute, we're asking that pump to push 8,334 pounds. That's over 4 tons that we're asking that pump to move. So this is why, as your flow goes up, your horsepower requirement is also going to go up. Now, of course, the opposite is true, too. As our flow goes down, our horsepower requirement is going to go down. If we go all the way over to the left-hand side of the curve, at zero flow, you'll notice that our horsepower is running, maybe 2.25 or so. All right? That's because all we're doing is just holding that column of water in a vertical position. How do we know what horsepower is, especially with an electric motor? And of course, one way to measure horsepower with an electric motor is your amperage reading. You throw an amp probe on there, and your grid reading on your amps. So what you're going to notice is this. As your flow goes up, your amp reading is going to go up. As you bring that flow back down, your amp reading is going to go down. All right? Now, the next thing that we want to look at on this curve, it's the last curve on this particular curve, is what we call NPSHR, Net Positive Suction Head Required. Okay? Remember, it's the amount of head required by the pump to keep the fluid in a fluid state. That's what we're looking at here. It's red over here on the right-hand side of the curve in feet of head, because remember, head is our energy source here. And of course, at our flow rate of 87 gallons a minute, you're going to notice we come off to the side here, and my guess is we're probably somewhere around 18 feet. Now, what exactly does that mean that we're at 18 feet? Well, remember from our previous webinars that when it comes to lifting water, centrifugal pumps have approximately 25 feet of lift at sea level. So, of course, if we were to go ahead and subtract that 18 feet from the 25 feet, that leaves 7 feet. 7 feet to do what? 7 feet to design the suction side of the pump. Now, when we talk about that suction side of the pump, remember what we said. The suction side of the pump is made up of two things, friction loss and vertical lift. Both of those things together are going to equal your total suction lift. Okay? So the next thought here then is, what if we're at 55 gallons a minute? You'll notice that we come right straight across there. We're probably about 16 feet ahead now. And of course, if we go to that maximum flow that we talked about, staying within our range of 120 gallons a minute, now we're somewhere in the vicinity of about 22 feet ahead. So what did we just learn? We just learned that NPSHR is also dependent upon flow, and that as the flow changes, so will the amount of head required by the pump to keep the fluid in a fluid state. It's very important that we understand we cannot change NPSHR. It is a factor of the pump. It's built in there by the engineer, and you cannot do anything about it. You can, of course, change your NPSHA, which we'll talk about in just a minute. However, before we talk about that, we're going to go back to this curve again. Remember, this is our recommended operating range, okay? But we're going to get rid of that. Why? Because we've got something different we want to talk about now. Now we want to talk about that curve right there. It's the 2.5 horsepower curve, all right? When we look at that 2.5 horsepower curve, we go all the way over to the left-hand side, we're going to find what we call the shutoff head. It sits right around 142 feet. Remember, shutoff head, as we just mentioned, is made up of two things, the suction side and the discharge side. That was in our last webinar. The suction side and the discharge side of the pump make up that zero flow at shutoff head. all right? Now, of course, I also mentioned last time that that's not going to change. It's always going to be the same, no matter what your suction lift is, no matter what your discharge pressure is, they're always going to add up to 142 feet. Obviously, always better. Now, as we move to the right-hand side of the curve, you notice that 10-gallon probably never going to change. 20, 30, 40, those numbers are probably always going to be the same. You will notice, though, that when we get out there at 70 gallons a minute, the curve changes. So we're going to get rid of that curve, and we're going to see what that change is, and you'll see it dips considerably at 15 feet of lift. What that means is, at 70 gallons a minute, the curve would be the same as if it was no lift at all. But once we get to that point where we've got 15 foot of lift, now the curve is going to change. Our flow ranges are going to drop off because we're trying to lift too much water too high. So you'll notice that your best efficiency, we said, on the max flow for this particular pump was 78 gallons a minute. It now has moved over to 75. And if you look at your maximum flow, it was 95. It's now moving over to 80. So there really is a very big important difference here, and we have to realize that. And of course, you'll also notice that if we go to 50 gallons a minute, the curve changes again, and now we are at 25 feet of lift. And of course, you'll notice we went from 95 gallons a minute down to about 62. So it's very important that we watch our lift. Now, of course, if curves aren't what you want to do, and of course you can see the curve doesn't show every lift to 25 feet. Most of the flow ranges that you're going to be working in will probably work at 25 feet, but what if you get beyond that point? What if I want to pump 60 gallons a minute? Okay, exactly how many feet could I get with it? So we've developed something called a box chart. Now, the box chart has all four pumps. There's your 1 horse, horse and a half, 2, and 2.5 horsepower pump. You'll notice right below there it says distance above water. Remember, that includes two things, your friction loss and your vertical lift. Each pump has 5 columns under it. The first column says 5 foot of lift. The last column says 25 foot of lift. All right? If you look over to the left-hand side, you'll see it says discharge pressure in PSI, and that ranges from a minimum of 10 to a maximum of 50. So the bottom line is, what you're going to do when you come to this chart to use it, you're going to say, okay, I want to use the 1 horsepower pump with 15 foot of lift, and I want 30 PSI. How many gallons a minute am I going to have? You simply cross those two, and you'll see you get 27 gallons a minute. And if we go back to our curve, we're going to find that at 85 feet, 15 foot of lift and 30 PSI, 30 PSI is about 70, so 70 and 15 is 85. At 85 feet of head, that pump will produce, as we cross the 1 horsepower line, about 27 gallons a minute. All right? So, yes, indeed, the chart is going to be the same as the curve. Now, remember I said you can't change NPSHR, but this is the formula for NPSHA. And you'll see it says PA minus PD plus or minus D minus F equals NPSHA. Remember, NPSHA is net positive suction head available to the pump. So, what does it all mean? Well, PA stands for the pressure over the liquid supply. Remember, if this is just open to the atmosphere, we're talking about atmospheric pressure. PD is very important because PV stands for the vapor pressure point of the liquid at that temperature. So no matter what the temperature of a liquid is, and we're talking water here, no matter what the temperature of that water is, that water has a flash point, a point from which it will convert from a liquid to a vapor. And in our last webinar, we talked about the fact that that happens no matter what if we drop the pressure over the liquid to that vapor pressure point. So that's got to get subtracted out of there, all right? Now, plus and minus Z. Z equals the static height above or below the datum plane of the pump. So the question is does the pump have a flood of suction, or are we working with a suction lift application? Okay? If we have a flood of suction, we're adding pressure to the pump. All right? Now, I remember one time we had a pump that was in Colorado Springs, Colorado, which sits at about 6,000 feet. The company that put the pump in, that installed it, was from here in Wisconsin, and they sent their team out there to put the pump in. Now, they wound up calling the salesman because they were having a little bit of a problem with something called cavitation. And, of course, the salesman, being from the area, realized immediately what the problem was. And he said, let's take a barometric pressure reading in the morning, and then let's take another one in the afternoon, because they were getting cavitation every afternoon. Well, of course, the problem was that every afternoon a low-pressure system would come over the mountains, and, of course, it would change the amount of NPSHA over that pump. By lowering that NPSHA, it created cavitation. So, of course, what wound up happening was they said, well, how do we fix this? And he said, simple. Just dig a pit where the pump is, put the pump about 2 feet down from where it sits right now, vertically, and you won't have a problem. And that's because they were able to change their NPSHA by lowering the pump. So NPSHA is something you do have an effect on. Can't change NPSHR, but you can NPSHA. Now that pesky F. In this case, F stands for friction loss. It's the head loss in the pipe on the suction side. And of course, it's going to be deducted from your NPSHA because it's going to be added to your lift. So however you want to do it, you can see it's going to affect how that pump is going to work. And this is why it's very, very important that you don't forget the friction loss on the suction side of the pump. All right? If those things added together, added and subtracted because you're doing some adding and subtracting, if those things added together equal or are greater than your NPSHR, you probably won't have a problem. But when your NPSHR is greater than your NPSHA, you're looking at cavitation problems. All right? Now, the next screen here is what we call the vapor pressure point of water. Now, of course, you'll notice it's at various temperatures. And so you'll see, if you look at the chart there, there's a column for temperature, a column for the absolute pressure, and a column for feet of head. If we go all the way over to the right-hand side, we're going to notice that at sea level, 14.7 psi or 34 feet of head, water is going to boil or flash at 212 degrees. If we take and move up to Denver, now remember Denver's at 5,280 feet, mile-high city, we're going to find that we're at about 12 psi, which puts us a little over 200 degrees to boil water. And of course, if at the eye of the impeller we get that pressure down to below 4/10, there's a possibility at 70 degrees that you can boil water. Now, this next slide here shows us the same thing, only in a chart form. All right? What it means is everything below that line is liquid. Everything above that line is a vapor. So if we go out to the right-hand side of the line and we draw a line right straight down, my guess is at 14.7 psi. And of course, we go over to the left-hand side from that same point, and my guess is 212 degrees, the boiling point of water at sea level. All right? Remember, if we go to Denver, we're at about 12 psi. 12 psi puts us a little over 200 degrees. If you've ever read the side of a macaroni box, it says that if you're going to cook this macaroni at altitude, you must cook it longer. Why? Because at 10,000 feet, water boils at 185 degrees, about 30 degrees cooler than sea level. So, of course, because the water's not as hot, it takes longer for the macaroni to cook. So you dump the macaroni into the boiling water and then let it sit for the same amount of time you would at sea level, you wind up with crunchy macaroni. Who likes crunchy macaroni? All right. Now, what if we get down to a half a pound of pressure? Well, there again, we can boil that water at about 70 degrees. So the bottom line is we need to be aware of this because something's going to happen in our pump. Now, what we just looked at was what we call cold water cavitation, converting a liquid to a vapor based on the vapor pressure point of the liquid so that at any temperature we can convert it. Now we're going to take a look at bringing water to a boil by heating it, raising the temperature of the water to the vapor pressure point instead of lowering the pressure to the vapor pressure point. But if you've ever read an owner's manual, it says if the pump does not prime in 10 minutes, turn it off and reprime it. Now, it doesn't say wait. It just says turn it off and reprime it. Why? Because in 10 minutes, nothing is going to happen. If you wait 12 to 15 minutes, now that pump could build up some steam in it, and when you go to take that priming plug out, it'll blow up at you. So you got to be a little bit careful. But 10 minutes, not a problem. So the bottom line is, if we wait here till our kettle's been on that fire there for about 12, 15 minutes, we're going to start to see what are called vapor bubbles appear at the bottom. Now, of course, you'll notice there, some of those vapor bubbles are going to break loose, and when they do, where are they going to go? They're going to go up to the top. That's what everybody says. Now, of course, Carrie, I want you to think about something here, okay? Where are we heating the water from? Bottom of the pot, okay? What about the water at the top of the pot? It's cooler. So what happens when the hot vapor bubble hits the cooler water? It implodes. It implodes. It implodes, yeah. It implodes and it turns back to water. As it implodes and turns back to water, that's going to be a very violent reaction. And so therefore, we're going to see some things happening. All right? Now, of course, once the water gets hot all the way through, then the vapor bubbles are going to go to the surface, and we're going to see them exploding. Now, the difference between imploding and exploding vapor bubbles. This is very important. Remember I said there's going to be a violent reaction when it implodes. Do this when you get home. Take a tea kettle. Hopefully you got a gas stove, because it works best with a gas stove. Fill the tea kettle up half, 3/4 of the way. Set it on the gas stove and turn it on. Now remember, you can walk away for about 10 minutes because nothing's going to happen in the first 10 minutes. Come back in about 12 to 15 minutes, though, and you're going to hear the vapor bubbles start to move off of the bottom. And as they move up and they hit that cooler water, they're going to go and implode. As they do that, if you've got this on a gas stove and you're watching, you're going to see the tea kettle is going to start to wiggle a little bit. It'll move around on that burner, okay? And that's because the violent reaction of that vapor bubble imploding. Now, of course, this is not the end of the experiment. This is the beginning of the experiment, because the point is, if we keep watching and we keep listening, there will come a point where the noise will go away, the rocking will stop, and we can amaze all of our friends and say, it's going to steam now. Okay, maybe we won't amaze our friends, but that's what's going to happen. Okay? Once the vapor bubble goes to the surface like this one has, and it explodes, that's not a real violent reaction. it lets off the steam, and of course we start to see the water vapor appear in the form of steam out of the kettle. All right? Now, of course, that's in a hot pot. We're talking about pumps, though. And so because we're talking about pumps, I want to talk about what can happen inside of the pump, because that pump is not going to let that vapor bubble get to the surface. All right? What's going to happen is this. If we do something called open discharge, open discharge means that at the pump, we're going to have a valve, and we're going to open that valve up as far as it will go. All right? Which means we're going to let as much water come out of that system as we can. Now, of course, remember what Bernoulli taught us. He said that if there's a smaller area, like the eye of the impeller, we're going to have faster moving water. And, of course, if there's a larger area, like the peripheral of the impeller, we're going to have slower moving water. Now, of course, remember the purpose of the impeller is to increase that velocity. So as we increase the velocity, we're also increasing the pressure by moving from the inside to the outside of the peripheral of the impeller. And as we do that, if we get this thing moving fast enough at the eye of the impeller, we will create cavitation. Those are not air bubbles, those are vapor bubbles. And those vapor bubbles are going to move through the impeller towards the outside, and as they get towards that peripheral, the pressure that's out there is going to start being applied to them. And as that pressure hits them, they're going to implode. As they implode, they are going to cause a shock wave, and of course that shock wave is going to accomplish several things. One of those things are holes in the impeller. Now, another thing that those shock waves can cause is it can cause the impeller to vibrate, and as the impeller vibrates, it's going to send that vibration down the shaft, and eventually you could wind up ruining the bearings. So it's very important that if you notice cavitation, you do your best to get rid of it. Remember, cavitation is 100% preventable. We just need to make sure we put enough back pressure on the pump. So if we don't do that, then we're going to have the problem of cavitation. All right? Now, of course, if we look at this next picture here, this is actual. This is an actual impeller, cast iron impeller. You can see in the yellow circles there the cavitation damage. Now, of course, the damage we're looking at is really kind of minimal, because if you were to be able to get inside, which is where the cavitation took place at, you would find the whole inside of that area in those circles is going to look like someone poured acid over it. All right? And again, I do want to point out, if you look carefully there, that yellow line there represents that vein. And you can see we are on the high pressure side of that vein. So, of course, that's why that vapor bubble got out here, couldn't remain vapor anymore, and we collapsed it. This particular impeller, just to tell you the story of it, was used in a farm application, and it was only used for 1,350 hours. The impeller is 18 inches in diameter, and at the time this picture was taken, which was a long time ago, it ranged about $2,000 in price. And so when we told the guy, you know, if you would just slow your water flow down, you wouldn't have this cavitation damage and you wouldn't have to be replacing this impeller so often. And he told us, you know what, I need the water, I don't care. Geez, I love customers like that. All right, when we get into piping, remember we were talking about the piping. You can also get cavitation in piping. Now, what happens is this. We would like to see the water flow through the pipe like that. Is that what's going to happen?
No.
No. Remember from our last webinar, we said that water had weight, it had momentum, and it had pressure pushing it. So all that water wants to move up and go through that one little area there. So we're reducing the area that the water is moving through. And as we reduce the area the water moves through, something is going to happen. What's going to happen? The outside of that elbow is always going to have higher velocity and lower pressure. The inside of the elbow, because there's not as much water moving through it, is going to therefore have lower velocity and hence higher pressure. Now, it's very important that we understand that it really doesn't matter what direction the elbow is facing. So if the elbow is facing this way, still the outside is going to be the high velocity, or it could be facing this way, and again, the outside is the high velocity. You look over it this way, and it's still the outside is the high velocity. So no matter which way it faces, the outside of the elbow is going to be the high velocity. And if that velocity gets too high, the pressure will lower to the point where we create cavitation, where we have a vapor bubble appear because the pressure is dropped to the vapor pressure point of the liquid. When it does that, that vapor bubble moves, and you can see it's moving to the outside edge of the pipe. Now, why is it doing that? Because down here on the inside of the elbow, we've got lower velocity and therefore higher pressure pushing it in that direction. So, what happens when the pressure in the pipe becomes greater than what the vapor bubble can handle? We wind up with cavitation damage. You can see here in the picture where the arrow is pointing, that's the curve, the elbow that's in the pipe, long sweep elbow. You can see that cavitation damage there. If you look at the left-hand front corner of that cavitation damage, you're going to see a white dot. That's a man. Okay? The cavitation damage is 115 feet long, 30 foot wide, 45 foot deep. It's a 50-foot tunnel. Okay? It's in the Arizona spillway at the Hoover Dam. Now, the best way for me to help you to understand what happened here, by the way, this picture was taken in 1941, is for me to go to the dam website and get this picture. So, this next picture we're going to look at, this next slide here, is showing you the Hoover Dam. There were two, there were two tunnels dug on the Arizona side, and there were two tunnels dug on the Nevada side. All right? Now, of course, when they first created the dam, why did they put the dam there? Well, those tunnels were in an area where they had to be almost a mile long. And so this gave them a straight area where they could put those tunnels at. Why did they build the dam? Well, they built the dam simply because of the fact that, well, let's see, it was 1934, so we're in the Depression, and this gave the CCC something to do so they could hire a lot of people. So it put people to work, kind of like how President Obama started making roads, by the way, improving the roads that we would put people to work. All right? Let's see, what else happened? Well, if you look down at the bottom of the dam there are 17 turbines in there, which means they could now provide electricity to the area. And of course, Los Angeles isn't that far away, and Los Angeles always needs water. So by putting the dam here and constructing a pipeline from the Hoover Dam to Los Angeles, they now have a way to get water to Los Angeles. But while those three reasons are good, the real reason why they created the dam was because of the fact that they needed to control the floodwaters. Every winter, snow would collect in the mountains. Every spring, that snow would melt. It would all come down into the Grand Canyon, and of course the Grand Canyon is only so big, so of course that means that the water had to move faster to go through the Grand Canyon. As the water moved faster and the Grand Canyon opened up into beautiful farmland, the Colorado River was moving so fast that it actually changed the direction of the river every spring. The farmers never knew for sure which way it was going to go. So they told the government, if you could control the floodwaters, we could grow food. Now, it also happened that 1934 was the year of the Dust Bowl, and food was very much in need. So this was kind of a win-win-win-win-win application as they went ahead and they built the dam. Now, of course, as you can see in the picture here, there are also going to be 4 entrances to those tunnels. And what they did was they built little dams back there to force the water into the tunnels, and then they built dams on this side to force the water downstream. That gave them the opportunity then to put a pump between those 2 little dams and drain all the water out. Now they could dig down the bedrock and they could build the Hoover Dam. All right? Of course, water coming over the top of the dam would not have prevented flooding. And so, of course, they had to find a way to stop the water from coming over the top of the dam, and that's when they decided to come up with what we call the spillways. There's one on the Arizona side, and there's a matching one over on the Nevada side. All right? Now, if you look at the spillways carefully, you're going to see that they lead to this tunnel plug. All right? So the original tunnels, once they were no longer needed, at the entrances, they dropped a 90-ton door, and that stopped water from going through the tunnels. So now they could dig a tunnel down from the spillway into this tunnel, and they connected it with what's called a tunnel plug. The tunnel plug happens to be that elbow that we saw in the picture. Okay? You'll notice also that there are some pylons there. Okay? Between those pylons are some heavy steel doors. And so they kind of look like this. There's the pylons. And when they want to, they can raise those steel doors with hydraulics, and that will raise the level of Lake Mead by 9 feet. Now let's go back to some of our other webinars and remember that a cubic foot of water, which is 1 foot high, 1 foot wide, 1 foot long, is going to be 7.5 gallons. All right? So 7.5 gallons per cubic foot of water, and what we're going to do is we're going to notice that if you go across the crest of the dam, there is 1,244 feet. So if I take 7.5 gallons of water per foot times 1,244 feet, I wind up with 9,330 gallons of water. 1 foot back from the dam, 1 foot high, 1,244 feet across. That's about 1/4 of a mile. Now remember, they could raise the level of Lake Mead by 9 feet. So I'm multiplying 9,330 times 9, and I'm going to come up with 83,970 gallons of water. That's almost 84,000 gallons of water per foot. We're talking 1 foot back, 9 feet high, 1,244 feet across. All right? Now, of course, the next question that comes up is, how big is Lake Mead? So this is a shot from the Space Shuttle Columbia as it passed over the western United States. This is Lake Powell in southern Utah. Lake Powell supplies the water that goes through the Grand Canyon. And on the other end of the Grand Canyon, we're going to find Lake Mead. Now, can anybody see the Hoover Dam in Lake Mead? The answer is no. You're hundreds of miles away, and it's only 1/4 of a mile wide, and you can't see it. Keep that thought in mind, okay? Because Lake Mead is 110 miles long. So if I take 110 miles if I take 84,000 gallons per foot times 5,280 feet per mile times 110 miles, I wind up with 44,800,000 gallons of water. And you can't even see it in that picture because it's only 1/4 of a mile wide. And then in 1941, someone thought it was a good idea to close those spillway doors and allow 47 billion gallons of water to flow through that 50-foot tunnel. Now, one thing I didn't tell you on purpose is from here, the bottom of the tunnel, or the bottom of the entrance to the tunnel, to the tunnel plug, that's a 400-foot drop. A 400-foot drop is 180 pounds per square inch. And you have a 50-foot tunnel. That's a lot of square inches and a lot of weight of water that comes crashing down on that tunnel plug. All right? Now, the next thing we're going to look at here, we're going to get rid of that. We're going to take a look at the fact that I went to visit the dam one time, and I'm standing right there. I'm talking to a tour guide, and I say to the tour guide, how did you know you had a problem over there? In 1941, there was cavitation in that tunnel. How did you know it? Now, I'm an ex-Navy man, and I'm thinking to myself, this is like depth charges going on. So they must have felt the vibration. And the tour guide says, well, the story goes like this. There was a photographer standing over here taking pictures of the water coming out over there. Now, I want to put this in perspective so we all understand what we're talking about here, okay? From the opening in the tunnel to the tunnel plug, you can see, is 2,200 feet, not quite a half mile, okay? We already said it's 1,244 feet across the crest of the dam. That's a quarter of a mile. And if you look carefully there, it says 736 feet from bedrock to the top of the dam. Now, of course, we're looking here and we're saying, well, geez, you know, we're not looking at bedrock, we're looking at the water level, so it's not that. We can't really tell for sure how far out from the dam that photographer was standing, okay? And we can't really tell in the picture, is it wider or narrower from where he was standing to the tunnel. But I can tell you, you're at least a half mile away, all right? And here you are taking pictures a half mile away from a tunnel that's 50 foot in diameter, and you notice something. So you call one of the engineers over, and you say to the engineer, where are those rocks coming from? Now, mind you, you're a half a mile away from a 50-foot tunnel. Those rocks are boulders coming out of there. The engineer immediately realizes they have a problem, goes to the control tower and says, we've got to stop the experiment. It takes them 4.5 hours to get those doors back open so that they stop the flow of water going through the tunnel. And in that 4.5 hours, it created cavitation damage 115 feet long, 30 foot wide, and 45 foot deep. If you're not impressed yet, I want you to realize that this tunnel is made out of 3-foot thick concrete. So when those vapor bubbles imploded, they went through the 3-foot thick concrete and 42 feet into the bedrock. All right? Now, some of you might be saying, well, it's a nice story, it's kind of interesting, but how does it help me? I'm never going to work at the dam. Well, neither am I. Okay? But I did get a phone call one time from a guy who told me he was using a 70-gallon-a-minute pump for a sprinkling application. All right? He had a problem, though. The problem was every 3 months, 3 feet from the wellhead, he popped a hole in his pipe. Now, I just wanted to say to him, well, it's cavitation. But I couldn't because I knew that the next question he was going to ask me is, well, how do I prevent it? I can't help him prevent it because I don't know what's causing it. So I need to figure out what's causing it. So I start out by asking questions. And the first question I ask is, what's your gallons per minute? And he says 60. Now, 60 gallons a minute with a 70-gallon-a-minute pump, no, that's not going to be cavitation problem. I'll bet I know what it is. I'll bet it's his pipe size. So I asked him what size pipe he had, and he says 2 inch. Now all I have to do is look up in the friction loss charts, 2 inch pipe is 60 gallons a minute. What's the velocity? 5.7. Nowhere near cavitation. I have to have a velocity of at least 10 feet per second going through a piece of pipe at the elbow in order to have cavitation. So this is not cavitation. Well, if it's not cavitation, what is it? Let's keep asking questions. So finally I asked the question and I said, where's your check valve in the line? He said, oh, there's no check valve in this line. And I said, you do realize with no check valve in line, every time you turn that pump off, the water's going to go right back down the well. And he says, that's what I want. He was afraid of freezing. So my next question was, well, okay, if the water goes back down the well, that means every time the pump starts, it starts it from whatever the depth of the water is in the well. So how deep is that water in the well? And he says 10 feet. Now, all I have to do is go to the 70-gallon-a-minute curve, and let's start right at the top. I like to take the ruler, and I put the bottom edge of the ruler right at the top of the curve. Okay? Now all I do, we're at 600 feet, I start moving that ruler down. So I come down to 500 feet, then I come down to 400 feet, then I come down to 300 feet, and then 200 feet, and then 100 feet, and that little line right there, that's got to represent 50 feet. Where am I going to? 10 feet. At 10 feet, I'm pumping a minimum of 120 gallons a minute. Minimum of 120 gallons a minute. So if we go back and we apply this 120 gallons a minute to what we learned in some of our other webinars, we know that if we double our flow, what else is going to happen?
Oh, that'll double the velocity.
That's right. And so now we notice that our velocity is 11.5, well over the 10 feet per second we need. And so therefore, that's our cavitation problem. Now, of course, there are some solutions. Actually, there's 4 different solutions for this particular problem. Of course, the first is put in a check valve. You put in a check valve, and of course, that means that you're going to keep water right out to that sprinkler system, and every time the pump turns off, the water will be right there. When it turns back on, we go right to 60 gallons a minute. Okay? The second solution is larger pipe. If I put in 3-inch pipe at 120 gallons a minute, the velocity is only a little over 5, about 5.1, less than what I've got now even. So I could put larger pipe in. Of course, that's a little expensive, especially since I've already got all this 2-inch pipe in. All right? Another solution would be, let's go ahead and put in a flow restrictor. Remember, the sprinkler heads themselves are the flow restrictors. So the bottom line is, if I put a flow restrictor in right there at the pump, now as soon as that pump starts up, it's immediately at 60 gallons a minute, and I don't have to worry about it. Okay, it puts the right back pressure on the pump, everything works just fine. All right? The third answer, or the fourth answer rather, is put in a variable speed drive. If you put in a variable speed or variable frequency drive, what you're going to be able to do now is you're going to be able to tell the drive, I want you to turn the pump on at half speed. Remember, at half speed, I'm going to get half flow. So half speed is 1,800 RPMs. Half flow is what I just happen to be looking for, 60 gallons a minute. So I say, stay at half speed for a minute, and then once you get up to a minute, then you can go ahead and go to